In the last two videos, we looked at setting up a static route and setting up a gateway of last resort. Now, I have removed the static routes from here, although I have left the gateway of last resort for routers 1 and 3, which send anything that it doesn't know how to get to up to router 2. However, if router 2 got a packet, say, from the 1.0 network, it wouldn't know where to send it to get to the 2.0 network because it has no route to get there and no gateway of last resort set on router 2. So now we want to look at the third way of setting routes. Directly connected is the first way, and then manually configured or static routes is the second way. The third way is through a routing protocol. Now, a routing protocol allows each of these three routers to tell each other about the network it's connected to. Not real difficult on a small one. We can set static routes on a very small network. But if this were a very large network, it would be better to set a routing protocol. In order to set a routing protocol, we have to turn it on, and there are different ones we could turn on. RIP, which is Routing Information Protocol, EIGRP, Extended Internet Gateway Protocol, or OSPF, Open Shortest Path First, which is the one we're going to use in this class. So in order to do this, I need to turn it on. So let's go ahead and turn that on. I'm already in global config mode. So to turn on router OSPF, you can see I had it on before when I was testing this lab, but I'm going to type router OSPF. Now, that isn't enough to turn it on. I need a number here. In fact, let's type a question mark, and you see that I need a process ID, anything from 1 to 65535. Now, we're not going to study what the process ID does because that's a little more advanced concept, but just know that we need a number, and we need to make it the same here on all of these. Although with OSPF, it would actually work if we didn't, but we're going to go ahead and do that here. We're going to make it a 1. All right, I've got router OSPF. I've got OSPF turned on in router 1. The next thing I need to do is to advertise these three networks so that these routers know how to get to it. So let's advertise this 1.0 network. And the way we do that is the network command. Network 192.168.1.0. Now I'm not going to put for the /24, 255.255.255.0. For routing protocols, we need the wildcard mask. So we're going to invert that and make it 0.0.0.255. The last thing we need is an area. In fact, let's type the question mark here, and you see that we need an area command. So the word area. And then finally, we need a number from 0 to 429.496.7295, a big number. So we're just going to make it area 0. Now these areas have to do with units. So that all of the routers have to be within the same area in order to advertise each other's networks. But on a complex network, you can have different areas so that the routes don't spill out among each other. So we're just going to use area 0 for everything. This is what we call single area OSPF. All right, we have advertised that network. Now we need to advertise these two. Well, why? If these other routers are directly connected to them, why would I need to tell these routers about these networks? Well, the reason is, you notice that there's a hidden network. Router 1 can't see 192.168.4. Router 2 can't see 192.168.6, and router 3 can't see 192.168.5. So we have to advertise these networks so that all of the routers can get the information about all of the networks. So I need to advertise the 5 and the 6 networks. So let's do that. Network 192.168.50. And now instead of 0.0.0.255, you notice these are all /30s. So the wildcard mask for a /30 would be 0.0.0.3. Remember, the subnet mask is 255.255.255.252 for a /30. And so 255 minus 252 is 3. So it's 0.0.0.3. All right, that was the 5 network, and I need to tell it about the 6 network because that's also connected to this router. So now we'll do the 6 network, and we're done with those advertisements. Let's do the same thing on router 2 now. We will turn on router OSPF1 and then network 192.168.0.0. That's for this network up here in this corner, the 0 network. And the wildcard mask would be 0.0.0.255 because it's a /24 and area 0. All right, it also needs to know, they also need to know about the 4 and the 5 networks. So let's put those in there. 192.168.4.0 and the wildcard mask is 0.0.0.3 and then the 5 network. Done. All right, finally router 3. So let's turn on router OSPF1 network 192.168.2.0 0.0.0.255 area 0. All right, that's for this network over here, the 2 network. And then we also need to tell the other routers about the 4 and the 6 network. So let's do that. There's the 4 network, except it should be 0.0.0.3 for a /30. And then the 6 network. Notice I'm using the up arrow to make these a lot easier. There we go. All of these should know about each other now. And let's take a look at the routing tables and see if this routing table has, it looks like it is doing something here. Yeah, it looks like it's setting up some OSPF adjacencies. So it is doing something. But let's look at the routing table. Show IP route. Yeah, and sure enough, now we have some OSPF going here. So let's see if we can figure out how to interpret this routing table here for OSPF. So all of the O's are OSPF routes. So we've learned, it looks like 3 different routes. And the first one we've learned here is 192.168.0.0 network. Okay, now this is this router down here, router 1. And so before it didn't know about this 0.0 network, but now it knows about the 0.0 network /24. And then we have a funky number over here. I'm going to get back to that in a minute. We know that we can get there by going to 192.168.5.1. That makes sense. It goes to 5.1 in order to get to this network. And then we have some interesting information. It also tells us what interface that's going to leave, and it's going to leave the S000 interface. All right, what's this number about? This first number is something we call the administrative distance. Every routing protocol has its own administrative distance, and the more reliable the routing protocol, the lower that administrative distance. Now, you may not know it, but static routes and directly connected routes also have an administrative distance. It's just that it doesn't show it to you. Let's see if we can go down here. Oh, yes, the default route does show you. This was a statically created route, and it has an administrative distance of 1. Remember, the lower the administrative distance, the more likely it is to use, I shouldn't say more likely, it will prefer routes that it knows through lower administrative distances. Now, why then would it use this route up here rather than the gateway of last resort? Well, because the other thing is, this is more specific. It looks at the most specific routes first. This one's a /24, where this is a /32. So it's a 0000. So, or not /32, but a /0, excuse me. So this is not very specific. It's a very general route. So it looks at the most specific routes first. And then it chooses the administrative distance, which is the lowest. And different routing protocols have different administrative distances. Static routes have an administrative distance of 1. And you don't see it here anywhere, but directly connected routes, both the C and the L's, have an administrative distance of 0. So the directly connected routes is the most authoritative, and then the statically created routes are the second most authoritative, and then routing protocols are the third most authoritative, and depending on the administrative distance here, the more authoritative it is. The second number here is the cost. So in the case of EIGRP, it looks at what type of line this is. Is this a gigabit line? Is it a fast Ethernet line? Is it an Ethernet line? Is it a telephone line? What kind of lines are these? And the faster the line, the lower the cost. So it looks first for the lowest administrative distance. Well, it looks first at the specificity, how specific is the address, and then at the administrative distance, and then at the cost. And that's how it chooses which route to take if there are conflicts, if there are overlaps here. So it's learned about the 00 network, the 20 network, and the 40 network. And let's do our ping now and see what route this thing takes. I'll turn on the simulator. Make sure we have ICMP traffic on, and I'll set up a ping here on this PC to 2.2. Let's raise this up. And now that it's set up, I'll click the run button and we'll watch this packet and see what it does. So it goes to router 1, now to router 3, and then up here to 2.2. So it took the fastest route. Why go all the way up here? If these are all the same, the cost is identical, so it's going to take the fastest route. By the way, the OSPF algorithm is very similar to the algorithm in your GPS. It tells you the fastest route to get somewhere along the roads. It looks at the speeds on the freeway and the speeds on the back routes and says this is the fastest way to get where you're going. So this worked just fine without any static routes. This is working real great. And we could look at the routing tables on both of these and it would look similar to what we saw on one, except of course different route numbers or different IP addresses.